I grew up in Nasik, near Mumbai, and like many Indians, big fan of cricket. But even when I was a teenager, watching cricket, always fantasized about how I can use the camera to tell the story in interesting ways. Fast forward to now, and I run a group called Camera Culture here at the MIT Media Lab. And as a professor, we invent a lot of great things in our group. All kinds of cameras. We have a camera that can look around corners beyond the line of sight. Or we have extremely high-speed cameras that run not at 1,000 or a million or a billion frames per second, but run at 1 trillion frames per second, where you can watch light slow down. Well, here in Boston, as you know, we are crazy for baseball, thanks to the Red Sox. So I really had to convince my students to give up their passion for baseball and focus on this really important problem of what happens in cricket. What did we do? We had so many problems. We had to figure out what kind of sprays we can use on a bat so that it may hide the signature of heat. Then we had to figure out how we can use a thermal IR camera, which looks like an ordinary camera but records the thermal infrared signature, to analyze the information that's coming from this imagery. And finally, we had to figure out how we can create very repeated motions on a bat so that we can figure out when the ball hits the bat in the middle, it nicks it and grazes it, or slides away from the bat. And to make very precise repeated motions for position and speed, we used a KUKA robot, which is a $30,000 robot, and is used for very different applications here at the MIT Media Lab. But we put that to use to see how a ball will impact the bat at different speeds and different locations. And finally, we use computer algorithms to reconstruct and analyze the different heat signatures to come up with a new conclusion. So here I give you my students, Everett, Stephen, Siddharth, and Chinmaya, who will show you how we did this experiment and came up with some really interesting results.
When the cricket ball comes in contact with the bat or the protective gear of the batsman, the friction due to this impact locally generates heat. This heat is a result of energy transfer between the ball and the bat. The heat signature is captured over a number of sequential frames by an infrared video camera and computationally processed to give these beautiful images. However, controversy has loomed over this technology, and we explore why. Last year, when India was playing England at Trent Bridge at the second test during the India's tour to England, a minor incident involving VVS Lakshman, former England player Matthew Vaughan, and Vaseline petroleum jelly got a lot of attention. However, it was proven by the inventors of hotspot technology, that is BBG Sports from Australia, that Vaseline, if applied on the edge of the bat, cannot hide the heat signature from the hotspot camera.
The main part of this project is on materials. Which material when applied may give you a heat signature, and which material when applied to the surface may not give you any heat signature. There are several aspects to be considered while applying materials for the heat signature detection. You have to consider whether the thermal conductivity of the material to be applied on the surface is lower than that of the air, or it is higher than that of the air. Consider the case of petroleum jelly or Vaseline. When applied on the surface of the bat, the thermal conductivity of Vaseline is 0.18 watts per meter Kelvin, which is much higher than that of air. As a result, Vaseline or petroleum jelly, when applied on the surface of the bat, will occupy all the voids on the grain structure of the bat, thereby giving you a denser grain structure or a denser material structure. As a result, the thermal energy transfers very easily as compared to what it would be in presence of only air. Hence, the heat signatures given off will be much uniform and better in resolution. But consider the case when the thickness of Vaseline layer is more than 1 mm. In such a case, there are alternate layers of air and Vaseline being tracked together. The resultant combination has a thermal conductivity which is much lower than that of the air. As a result, this combination acts as a thermal insulator thereby blocking all the heat signatures given off by the bat surface. Now the entire class of materials that we have proposed here are basically silicones and siloxanes, which are thermally insulating materials, which when applied to the surface of the bat give you a material which has a thermal conductivity which is very less as compared to that of the air. Hence, the heat signature given off by the bat is trapped between this material and the wooden grain structure of the bat. This heat signature or the dissipated heat is given off to the atmosphere via diffusion in the form of radiation. Thereby, thermal air camera is not able to detect any heat signature from the surface of the bat.
To test various conditions and materials, we use this robotic arm to simulate a thrown ball and a tipped hit. In this setup, we have the ball mounted to the arm, and we keep the cricket bat fixed on a vise mounted to this table. Using this setup allows us to precisely control the speed and the path that the ball takes. For example, here you can see the ball moving at 0.45 meters per second, 0.9 meters per second, and 1.8 meters per second. This KUKA arm is capable of a repeatability of around 0.03 millimeters, and we use it at speeds up to 2 meters per second. It's also a very flexible setup. Using this robotic arm lets us evaluate different factors, like the height at which the ball strikes the bat, and even the orientation of the ball.
Here we show how we emulate the situation on field, that is, when the ball hits the bat. Here a ball is mounted on an iron rod and smacked onto the bat, and the hot spots are clearly seen by the thermal camera. Note that no material has been applied onto the bat to hide the hot spot. Next, we apply silicone spray on the bat and image the same process using the thermal camera. Interestingly, no hot spots are seen on the bat after the silicone spray has been applied. Now that you've seen the robot and the ball and the bat experimented under controlled conditions, we are going to talk about the future of thermal imaging in cricket. During this exploration, we also identified some new applications that may be applied to the future of cricket, and specifically thermal imaging applications. Data analytics, answering questions like how many times did a batsman middle the ball, like doing a bowler's line and length analysis using Hawkeye, which is already very widely done in international cricket broadcasts. Where did the bowler bowl? How many times did the bowler bowl the ball in that length or along that line?
Can we utilize thermal imaging to develop higher quality bats and balls? To develop a metric to understand how many balls a batsman middles to improve training? New scanning technologies to test whether any surface has been applied to a bat before going to the field. The future of thermal imaging will have a deep impact on other sports as well: American football, soccer, and baseball. The potentials for science to expand how we understand our favorite games are great.